This presentation on hydraulic flow control valves is number 6 in a series of 8, which provides a comprehensive introduction to hydraulics, the science of fluid under controlled pressure. I'm Paul Cook for Vickers. In past discussions, we've talked about how we can control pressure in a hydraulic system and how we can control direction of flow. In this session, we'll discuss how we can control the rate of flow. By controlling the flow rate, we can control the speed of hydraulic cylinders or motors. To start, let's use a simple circuit, but include our old friend, the relief valve, to provide overload protection in case anything goes wrong. In this instance, the cylinder speed is determined by its size and the flow rate from the pump. A larger diameter cylinder would hold more oil and take longer to complete its stroke. A smaller one would, of course, move faster. Changing the flow rate from the pump would also change the extension time of the cylinder. Changing either the cylinder or pump size to regulate speed would be impractical, especially if we wanted to change speed in mid-stroke. A more typical method is to use a flow control valve. A flow control valve, in its simplest form, is nothing more than a variable orifice. It could be as basic as this needle valve. By varying the size of the opening, we can vary the amount of oil entering the cylinder and thus control its speed. Here we have a fixed displacement pump, a relief valve, a variable orifice or flow control, and the cylinder. If the pump delivered 10 gallons per minute and we wanted to cut the cylinder speed in half, we would adjust the flow control to pass only 5 gallons per minute. However, since it's a fixed displacement pump, if we allow only 5 gallons per minute to pass through our flow control into the cylinder, the other 5 gallons have no choice but to go over the relief valve at the relief valve setting. If the relief valve happened to be set at 1,000 psi, a pressure gauge at this point would read 1,000 psi. The pressure we see at this point would be determined by the workload on the cylinder. The difference between the two readings is called the pressure drop across our orifice. That's the pressure required to push the 5 gallons per minute through the orifice. We refer to this as meter-in circuit. That is, we're metering the oil going into the cylinder. However, meter-in circuits can only be used with opposing loads. If the load in this example should tend to run away, it would pull the cylinder ahead of the oil supply, and since the exhaust flow has a free path back to tank, our meter-in circuit would not prevent the load from running away. In this instance, let's put the flow control on the outlet side of the cylinder. In other words, we'll control the flow coming out. This is known as a meter-out circuit. Now, if we were to close the flow control completely, the oil could not exhaust from the cylinder, and it couldn't move. By regulating the size of the opening, we can control the flow rate and thus the speed of the cylinder. If this happened to be a 2-to-1 ratio cylinder, and we were controlling the flow rate out to the tune of, say, 3 gallons per minute, then the flow rate into the other side would be 6 gallons per minute. But we have a 10-gallon per minute pump, and here, too, the other 4 gallons would return to tank over the relief valve. And our pump would be operating at the relief valve setting regardless of how easy or difficult it was to move the load. We now have 2 ways to apply a flow control. Metering into the cylinder is fine with an opposing load. But if the load tends to run away, our best bet is to meter out. In fact, a meter-out circuit works if the load pushes or pulls. This probably accounts for the saying, when in doubt, meter out. Remember, though, both meter-in and meter-out circuits require the pump to operate at the relief valve setting. Now, there's one more way to apply a flow control. We could simply tee it off the main line like this and still control the cylinder speed. For instance, With the flow control completely closed, the full 10 gallons per minute from the pump would go into the cylinder. However, the moment we begin to open this up, we begin to bleed off some of that pump delivery, and the cylinder starts to slow down. So, by adjusting the size of the opening, we can bleed off any amount necessary to control how fast the cylinder moves. This is known as a bleed-off circuit. In this case, unlike the meter in or meter out, there is no excess flow going over the relief valve, and our pump operates at only the pressure that's needed to move the workload on the cylinder, and this saves energy. The bleed-off circuit will not prevent it from running away. As with a meter-in circuit, we'll have to use it with opposing loads only. The bleed-off circuit is not as accurate as meter-in or meter-out because the measured flow is to tank rather than into the cylinder, making the cylinder speed subject to changes in the pump delivery and leakage rates as the workload pressures change. To minimize these effects, it's recommended that we do not bleed off more than half the pump delivery and not apply it where there's a wide fluctuation in the workload pressure. Just to recap a little bit, we have the meter-in circuit where we have the flow control measuring the oil into the work cylinder. If we had an overrunning load condition, we could put the flow control on the exhaust side of the cylinder to restrict the flow coming out. And we have a meter-out circuit. If our speed requirements don't have to be too exact, we can take advantage of horsepower savings and use the bleed-off circuit where the excess flow goes to tank through the flow control rather than over the relief valve. Now, let's take a look at a situation where the workload changes. The valve that we've been using up to this point is just a plain old needle valve, something like the faucet on the side of the house. Let's say we have the flow control adjusted for 5 gallons per minute. The other 5 gallons go over the relief valve at its setting. The pressure at the relief valve is 1,000 psi because that's where the valve is set. The pressure at the cylinder will be determined by the workload. Assuming a workload of 2,000 pounds and an area of 10 square inches, the pressure on the cylinder side of our orifice is 200 psi. We learned earlier that we must have a pressure difference across an opening to cause flow through it. And in this case, with pressures of 1,000 and 200 psi, we have an 800 psi pressure difference. Now let's assume the workload changes. Maybe we have a pressing operation where the density of the material increases. This represents an increase in the workload. Let's say those workload forces go up to 4,000 pounds. This means our pressure here goes to 400 psi. However, this pressure is still fixed at 1,000 psi, the relief valve setting. The pressure difference across our orifice now is only 600 psi, and the question is, will 600 psi push as much oil through that opening as the 800 did? And the answer is no. Let's see why. Here we have a tank filled with oil, and in the tank I've drilled 3 holes all the same size. Now taking a look at our diagram, we see that the flow out of the bottom hole, A, is the greatest. The next greatest is B, and the least is C. Why do we have the greatest flow rate at A? The answer is simply because of the height and the weight of the fluid. The pressure at A is greater than it is at B or C. So, in a hydraulic system, if we can keep the same pressure difference across a given size orifice, the flow rate through it will be the same. Now, let's go back to our other diagram. Now we see here, when the workload went up from 2,000 to 4,000 pounds, the pressure went up from 200 to 400 psi, decreasing the pressure difference across the orifice from 800 to 600 psi. This means the flow rate has decreased and the speed has decreased. If we want to keep a constant speed in the event of changes in the workload pressure, a needle valve simply won't do the job. We'll need a pressure-compensated flow control. What we've done here is teed off the main line to a little spring-loaded poppet. Let's assume that the spring force here requires a pressure of 20 psi on this area to overcome it. Let's also assume that the load on the cylinder is practically zero. We have a 10-gallon per minute pump, and the flow control is adjusted for 5 gallons per minute. Now, when the oil comes out of the pump, only 5 gallons per minute can flow through the orifice. So the buildup in pressure, once it reaches 20 psi at this point, will cause this poppet to move off its seat, and the excess flow from the pump will take this path through here to tank. So we would have 5 gallons per minute taking this path, the other 5 moving the cylinder. With pressure at this point 20 psi and the pressure at this point 0, assuming no load, the pressure difference across our orifice is 20 psi. Now let's say that the workload pressure increases to 10 psi. The pressure at this point is 10 psi determined by the workload. The pressure at this point needed to open this valve is still 20, because again, all we're pushing up with is a spring that's worth 20 psi. So, our pressure difference across the orifice is now only 10 rather than 20 psi, and the flow rate through that opening is reduced and the speed of the cylinder is reduced. What we want to do is have this pressure increased by the same amount as the increase in workload pressure. To do that, we just tee off a sensing line from the workload side of our orifice into this spring chamber. Now, whatever pressure we have here works on the area of the poppet on this side, adding to the spring load. With pressure of 10 psi plus a spring that's worth 20 psi, the pressure required to open this valve and bypass the excess will have to be 30 psi. What's the pressure difference across the orifice? Still 20 psi. And 20 psi gives us the same flow rate and consequently the same speed. If the workload pressure increased to 100, we would have 100 psi aiding the spring. 100 plus 20 psi would mean that this pressure would have to go to 120. The pressure difference across our orifice would still be 20 psi, and the flow rate would still be the same. Increasing or decreasing the orifice size would enable us to increase or decrease the cylinder's speed as needed. By keeping the pressure difference across the orifice the same regardless of changes in the workload pressure, we now have a pressure-compensated flow control. This is actually what we call a bypass-type flow control valve. A bypass-type flow control valve is used only in a meter-in circuit. It will not hold back against overrunning loads, nor can it be used in a bleed-off function. So this valve is limited to one application, meter-in, but it has an advantage. If you recall, with a meter-in circuit or the meter-out circuit, using the plain needle valve, the excess oil went over the relief valve at the relief valve setting. With the bypass type, the pressure at the pump is just 20 psi over what the workload is. If the workload were 400 psi, the workload pressure back at the pump would be 420. So, comparing it to the meter in or meter out that we looked at just a little while back, it's saving energy for us. There is something else we can do with our bypass flow control. When this cylinder reaches the end of its stroke, we'll need some type of overload protection, and a flow control of this type can be modified to include a built-in relief valve. To do that, we just limit the pressure in this spring chamber by means of a small poppet and an adjustable spring. If I set this for 980 psi, it limits the pressure in the spring chamber to 980. Add to that the 20 psi for the spring, and the most pressure we can have once the cylinder reaches the end of the travel is 1,000 psi. So we could put this all in one package and have a combination overload relief valve and pressure compensated flow control. Because of the relief valve, it would have to be mounted between the pump and the directional valve, which we haven't shown here. It has the advantage of saving energy in that it doesn't operate at the relief valve setting when we're controlling speed. The disadvantage is that it can only be used in meter-in applications because the excess fluid is bypassed directly to the reservoir. Now, let's take a look at a pressure-compensated flow control that can work in a meter-in, meter-out, or a bleed-off function. Here, too, we maintain a constant pressure drop across an orifice, but in a somewhat different manner. We call it a restrictor type. It can be used in all three applications: meter-in, meter-out, and bleed-off. This spool will move up and down in response to workload changes to keep the pressure difference from here to here constant. So we'll call it the compensator spool. The adjustable orifice controlling the flow rate into the cylinder controls speed, and we'll call it a throttle. Up here we have our old friend, the 20 psi spring, holding the compensator in the open position. If the pressure underneath this spool reaches 20 psi and tries to exceed it, the spool will move up, tending to close off flow into the valve. Again, let's assume we have a 10-gallon per minute pump and we only want 5 gallons per minute into the cylinder. When we turn the pump on, flow through the throttle is restricted and pressure builds up here and under the compensator spool, moving it up against the spring. As it moves up, the opening gets smaller, and as it gets smaller, it restricts the flow rate entering the valve to what 20 psi can push through the throttle. In our case, 5 gallons per minute. The excess flow again must return to tank over the relief valve. If the relief valve were set for 1,000 psi, the pressure at this point, when we're controlling flow rate and speed, would be 1,000. The pressure at this point would be determined by whatever the workload is. If the workload pressure were 100 psi, we would have 100 psi here, and we'd have 1,000 psi here. Now, how much would we have here? Well, let's take a look. We have a sensing line from the workload side of the cylinder, and whatever pressure we need to move that cylinder adds to the 20 psi spring. So the pressure here will always balance out the spring force plus the workload pressure. We have 100 psi plus a spring that's worth 20. So the pressure at this point will be 120 psi. The pressure difference across the throttle is 20 psi, and the flow will be 5 gallons per minute. If the workload went to 400 psi, this would go to 420. Now, what's the pressure difference? Still 20 psi. And the flow rate? Still 5 gallons per minute. And the speed remains the same. Now let's take a look at a flow control that has an additional benefit. We all know that the temperature of oil affects its viscosity. We can get more hot, thin oil through an orifice at a given pressure than we can cold, thick oil. Any change in the temperature of the oil changes its viscosity, which in turn changes the rate of flow through our flow control and the speed of the cylinder. Now here we have a drawing of a pressure-compensated flow control with a temperature-compensating throttle. Its operation is essentially the same as the previous valve. Here's our compensator spool. Now instead of having the sensing hole in the body, at this point we simply sense the pressure to the bottom of the spool through this hole. Instead of using the graphic representation for the throttle, we'll show a more realistic one. It's sort of a cup-shaped device with V notches for better metering. It's held open by a small spring and closed by an aluminum alloy rod, which extends through the cup into the oil flow. If we'd set this for 6 gallons per minute and the temperature went up, the oil would become a little thinner and tend to flow faster through the throttle. However, the increased temperature also causes the aluminum rod to expand and close the throttle opening to compensate for the change in oil viscosity. So, even with the thinner oil, the speed still stays essentially the same. So, there are really 3 possible locations for the flow control. Where it's located is determined by the requirements of the particular application. Well, we've spent a lot of time on theory and schematics. Now, here's the actual hardware. Here again is our simple needle valve. This one's a non-compensated flow control. It's adjustable, and it has a check valve built into it for reverse free flow. It's installed in the circuit by means of threaded pipe ports. Now this is the unit that's both pressure and temperature compensated. The knob on the front allows us to set the throttle opening, and the key is a means of locking the setting. The valve is installed into the system by means of a subplate which has matching in and out porting. Over here we have a feed control panel, which in effect is two flow controls. This package allows the cylinder to have a rapid advance and coarse and fine feed cycles. It too is installed into the circuit by means of a subplate. No oil lines are connected directly to the valve body. And finally, we have a large valve which can be electrically modulated to allow us to control flows up to 60 gallons per minute. Okay, that concludes our discussion of flow controls. As you've learned, the speed of an actuator depends on how much oil is pumped into it, and flow controls regulate that speed. This has been Chapter 6 in our 8-part training series on the basics of hydraulics. I'm Paul Cook for Sperry Vickers.